Welcome back to another video lecture for a series that I'm doing on number theory. And in this part 2 of this series, we'll be discussing the divisibility rules. And divisibility is one of the most important concepts in number theory. So we need to establish several definitions and techniques that we will use throughout the congruence section of number theory, and these techniques can be used in several of the constructive proofs that we're going to look at. So first off, we need to establish a definition of what we mean by divisibility. So suppose that we have two integers, a and b, and furthermore, we need to state that a does not equal to 0 for the purposes of this definition. Now, we can say that a divides b, which we denote with this vertical bar in between the two, that's a divides b, if we can find some integer k so that b is equal to a times k. So if we cannot find such an integer k, if there does not exist a integer so that b can equal a times k, then we can write that a does not divide b, which we denote with this same vertical bar with a line through it. That's a does not divide b if there is no such k so that b is equal to a times k. So another notation in this divisibility set of notations would be if we have a to some power n double divides b, what that means is that a to the power n divides b, but a to the power n plus 1 does not divide b. In other words, a to the power n is the largest such power of a that will divide b. So some examples, we can say 3 divides 12 because 12 is equal to 3 times 4. Note we can find some integer that will allow us to scale up the first number to equal the second number. We can say 3 does not divide 7 because 7 is a prime number, and therefore there is no such integer that I can scale up 3 by in order to equal 7. And we can say things like 2 to the power 3 double divides 8 because 2 to the power 3, which is 8, obviously divides 8, but 2 to the power 4, which is 16, does not divide 8 because there exists no such integer that allows me to scale 16 to 8. Now there are several properties that we need to be aware of when we are dealing with divisibility. First of all, divisibility is a relationship of partial order because of the following three things. First of all, we know that a divides a. This is what we would call reflexivity. In other words, a number divides itself. Secondly, we have some notion of transitivity like we do with equality, where if a divides b and then b divides c, we can say that a divides c. Lastly, we have the property that if a divides b and b divides a, the only way for a number to divide another number and then to flip that division is if those two numbers are the same thing. So a is equal to b if a divides b and b divides a. Another important proposition when talking about divisibility establishes 4 more properties that are worth mentioning before we move into any of the proofs in this section. So if we pick several integers, we'll call them a, b, m, n, d, and these are integers, and furthermore they must be positive integers. Then there are 4 statements that we can construct, 2 of which are given with proof and 2 of which I will kind of omit the proof because I think it should be fairly obvious why this is the case. The first one says, if d divides m and d divides n, then d will divide am plus bn. So there's a couple of things happening here. First of all, notice that we have an assumption that our integer d already divides m and n, and so that means that the integer d will have to divide the linear combination of a scale multiple of m and a scale multiple of n, where a and b are the scale factors. So the proof is given as follows. First off, d dividing m means, by definition, that I can find a way to construct m by taking d and multiplying it by some constant. Similarly, with d dividing n, we can construct n by d times some other constant. Now notice here that the constants are integers, and we don't necessarily have to state whether they're positive or negative integers. However, notice that in the initial assumption we're saying that a, b, d, m, n are all positive integers, so it makes sense that k is most likely some positive integer. So am in our final statement will actually equal to a times dk1, and bn will equal to b times dk2. Now notice here that the linear combination am plus bn will actually equal to a dk1 plus b dk2. As a result, we have a factored version of this that we can write, which is d times ak1 plus bk2. Notice here that since a, b, d, k1, and k2 are all integer numbers, and we are only using the operations multiplication and addition on that group, what we have is a closed situation where all of this stuff underlined in the blue is just some other integer. So that is d times an integer, which is the definition of our divisibility. So in other words, d divides am plus bn, and that is the proof. So again, what the statement says, the result that we can use here from this proposition, is if d divides two integers m and n, then it must divide a linear combination of a scale multiple of both of those integers. And scale up m by a, scale up n by b, d must divide the linear combination of those two numbers. The second statement, which is given without proof, should seem fairly obvious just by thinking about it a little bit, and then we'll see part of the reason why this works in the third statement, because we're going to kind of work backwards from this. So d dividing n means that a times d will divide a times n, and you can kind of think about why that must be true. Of course, if you were to scale the top and bottom of a fraction by some particular value, and it's the same value, it's like multiplying by 1 so you get an equivalent fraction. It's basically what this thing says right here. The third statement, we're going to just reverse the direction of this. So the third statement says that if we have AD divides AN, then that's going to mean that D divides N. And there's a pretty nice proof for this, which should bring to light the reason why the second proposition works in the first place. Notice that AD divides AN means that we can find some way to make AN by multiplying AD by some constant that we will call K. And recall here that K is some type of integer here. Now, furthermore, notice that we have we can subtract the K times AD from the right-hand side to equal AN minus ADK equal to 0. And again, we can factor here. A is equal to N minus DK, which is equal to 0. Notice here that since a cannot equal to 0, since we're using a as some sort of scale factor, a cannot equal to 0, what that means is that n minus kd must be the portion of this expression that equals to 0. So we can just consider that part, n minus dk equal to 0, which is that n equals to dk. In other words, I can scale up d by some constant k in order to equal n, which is precisely the definition of d divides n. So we can say that d divides n, and that is the end of that proof. Now the last statement given without proof is this thing right here, and it says a fact that should seem fairly obvious again. It says that if d divides n, well then what's left over when you divide n divided by d will also divide n. You can think of this pretty easily by a quick example. Take the number 35, for example. If we wanted to divide 7, so 7 divides 35, then whatever the leftover is, the other number that is a part of that multiplication fact, 7 times 5 equal to 35, it must also divide n. So if I take 35 divide 7, I get 5. 5 must also divide n. And of course we know that we can write 5 divides 35 because 5 times 7 is equal to 35. On to one of the most important results in this part of number theory, the divisibility. So we have Euclid's division algorithm. And Euclid's division algorithm is extremely important because it is actually one of the reasons why when we teach third graders how to do long division, we do the process that we do. So notice that we have to kind of phrase this a different way because again in this part of number theory we're still only considering the groups of integers and natural numbers under addition and multiplication, and so we don't do things like perform divisions to arrive at our point because what we're trying to do is show how to divide things. So we can't use division to show how to divide. So what we have is a statement that says that for two integers, and these are typically positive integers, we can find a unique q and r, and that's quotient and remainder, within the integers so that our one number j would be equal to q times the other number k plus r. And furthermore, it's of note that this remainder has a couple of cases that could happen. We could get a remainder of 0, or we could get a number. And there are some limitations on what that number can be. First of all, if we get a remainder of 0, then we simply say that k divides j, because we will have the definition of divisibility by simply covering up this remainder of 0, j equals qk. In other words, there is some integer q that I can scale k up by in order to equal j, and so that means that k divides j, if the remainder is 0. Next, if we go through the motions here and we find a remainder, that remainder will always be less than the number that we are attempting to divide here by. So if I'm trying to divide j by k, the remainder can never be bigger than k, because what that would mean is we would add one more to the quotient and then we would reduce the remainder to something that was smaller than k in the first place. Now there are two parts to this statement that we'll need to talk through in order to establish a proof, and they are right here in this statement. First off, we have to establish that we can find a quotient or a remainder. That's an existence sort of proof. And the other thing is the exclamation mark, which means unique. We have to prove the uniqueness of such a quotient and remainder. And you can do this in any sort of order, but I think maybe the easiest way is to do the part that is easy first and then do the part that's a little bit harder second. So I like to tackle the uniqueness portion of this first. And we'll do that by way of contradiction. In other words, we're going to show what would happen if there was not a unique quotient and remainder for this particular type of division. So we're going to start by assuming to the contrary that we can express j both as qk plus r and as q1k plus r1, where q1 and r1 are not equal to q and r. Okay, so we still have to follow the rules here. Both of the remainders will follow the same rule, which is that they must be in between 0 and k or equal to 0. And I think you can kind of rationalize through this example. If there was a different quotient and a different remainder, then you would have some situations where you would find something that says that there's a remainder of 2 and also a remainder of 0, because remember that remainder value can take any value between 0 and up to k. So that would be a contradiction, and you can kind of see where we're going with this part of the proof, because if you had a number which was a multiple of a different number, then you wouldn't be able to say that in a different representation it's not a multiple of that number and therefore we have a remainder. So that wouldn't make any sense to say, oh yeah, if you look at it this way we get a remainder of 2, but if you look at it this way, well then it's a multiple of something else. So that doesn't make any sense, and it should seem pretty obvious going forward what we're going to attempt to do here. Okay, so if we reorganize these two equations just a little bit, what we can come up with is that r minus r1 will equal to k times q1 minus q. And we achieve that by just subtracting qk over to the right-hand side and r1 over to the left-hand side here. And then we're going to look at what this result leads us to. Now, obviously the remainders here are already less than k, so subtracting the remainders, and if we get a negative value, we can just take the absolute value of that to look at what that remainder must be. They will always be less than k. So it seems here that we have this part is obviously less than k. But also notice that q prime and q, they're like integer numbers. So if we look at the absolute value of the subtraction between q1 and q, at a minimum what we end up with is a situation, remember that these quotients cannot be 0, because the only way that that happens is if we were dividing 0 in the first place. So q1 minus q must be some integer value, 1, 2, 3, 4. And if we consider the absolute value of this, then any multiple of k must either be k or it must be bigger than k. So it would seem that this part right here is saying that it is either greater than k or equal to k. Now notice here that this statement is effectively saying that k is greater than k, because we know here that if this value on the left-hand side must be strictly less than k, and this value on the right-hand side could be k or it could be bigger, then the only way for that to happen is for k to be greater than k. In other words, we've arrived at some kind of contradiction here. The only way for this to happen is if r minus r1 and q1 minus q is precisely 0, and then we wouldn't be allowed to divide there because we would have a quotient that is 0. In other words, they are the same number. So here's our contradiction. If we had two different representations, it would lead us to wild conclusions unless q1 and q are the same thing, and r1 and r are the same thing. In other words, these must be precisely 0 in order for this statement to make any sort of sense. Okay, so the second part of the proof, we have to establish that there exists a unique r and q. We covered the uniqueness part, so we need to just establish that there are r's and q's that we can find for this particular type of situation. So to do this, what we're going to do is we're going to consider the following set. This is the set of numbers that can be written as j minus x times k, with x being drawn from the integers, so that these numbers are either 0 or positive. So they happen to be non-negative, and they could be 0, but we notice here that there's a few simple things that will happen here. as we start examining this set. First off, if we call this object j minus xk equal to r, then we know that r must be either greater than or equal to 0, but less than k. Now, of course, we have that 0 is less than equal to r, because by construction, r being an element of this set, we've shown by construction that it must be either greater than 0 or 0. So of course we have that part of our condition at this time. So it's also pretty easy to see that if r were greater than or equal to k, then S would contain the element r minus k, which is less than r, because of the following fact. Excuse me. Excuse me. 0 is less equal to r minus k, which would be equal to j minus qk minus k but then notice here that j minus qk minus k would be precisely equal to j, which is equal to, I'll come down here to do this next part, which is equal to j, which is equal to q plus 1 times k, which is in our set S. As a result, r would not be the minimal element of S, and we know that by construction we need to find a minimal element of this set. Okay. A quick example of how we can use Euclid's division algorithm to divide a number and find a quotient and a remainder. What we're trying to do here is we're going to look at the multiples of 45. This is 768 divided by 45. We want to look at the closest multiple of 45 to 768 and then find how many more we must add in order to equal 768. And it turns out the closest multiple is 17, which leaves us off by 3. So notice we are able to find both a Q and an R, and they are unique, that will make this particular statement true. So now we need to look at the idea of a common divisor. The definition for a common divisor is that if we have some integer d, it will be a common divisor of a and b if d divides a and d divides b. And furthermore, if at least one of a and b is not equal to 0, then there are only finitely many common divisors. In other words, this list terminates somewhere. You cannot find infinite amounts of things that will divide numbers. The largest such divisor is called the greatest common divisor of a and b, and we can denote that a couple of different ways. In algebra, we used to write GCD of a and b, but in number theory, a lot of times we just omit the GCD part because it is understood that a comma b is asking you for the greatest common divisor of a and b. Now, there's some properties with the greatest common divisor. First of all, GCD of a and b, this switching effect, if you switch the location of the a and b, it does not matter. The GCD will still be the same. Next, the GCD will always be, except in two cases, greater equal to 1. And the two cases where it will not necessarily be greater equal to 1 are when you have zeros. So if you have the GCD of a and 0, then this will precisely equal to whatever the magnitude of a is. And if you have the GCD of 2 zeros, then this is going to be undefined. And you can think about that pretty easily because that would require 0 to be divided by 0, which we don't know how to do from algebra. Now, of course, we're not talking about limits or calculus, and so we just simply say that this is undefined. So some examples for this. We could say the GCD of 6 and 27 is 3. And there's a couple of different ways that we could achieve this. We could list all the factors in a list for 6 and in a list for 27 and find the greatest number that appears in both lists. And that's totally fine for small numbers. The bigger numbers, however, we are going to use an alternative method to find the GCD. So we could also say the GCD of 1 and 10 is 1, and then the GCD of 22 and 0, by this definition, is just the magnitude of the number given, 22, that is non-zero. Now this next theorem has to do with the way that we can express a greatest common divisor. So the theorem says allow b and c to be numbers so that b is not equal to 0, and these are integer numbers again. Then the GCD of b and c has to be the minimum element of this set here, which is bx plus cy with x and y drawn from the integers and the natural numbers. So to prove this, what we're going to do is first establish this set that we've been given. It's bx plus cy with x and y drawn from the integers. And there's a couple of cases that can happen here. Note that b cannot equal to 0 by the theorem. So the only two cases we need to consider are the first one where b is greater than 0 and the second one where b is less than 0. If b is greater than 0, then b will equal to b times 1 plus c times 0, which is a positive element, b. And if b is less than 0, then we can express it as b equal to b times minus 1 plus c times 0, which again is greater than 0. This establishes that S has at least one positive element. That means that we will be able to find a minimum value of this set because we will always have at least one positive element. So in the next part of this proof, we're going to show that the minimum element of this particular set is the greatest common divisor of b and c. And to do that, what we're going to do is say that the greatest common divisor b and c is equal to d, and then we're going to suppose that we had some minimal element, which we'll call L, and that's the smallest positive element of S. That means that L can be expressed as bx0 plus cy0. And x0 and y0 here, again, they must be integers. So we're going to do this by way of contradiction. Suppose that L does not divide b. So by the division algorithm, we know that there's going to be some quotient and some remainder, because had it divided b, then the remainder would be 0. Now, of course, we know that the way that we can express this remainder will be r is equal to b minus L times q. Now notice here, because we have the ability to express L as this bx0 plus cy0 from the proposition, we can write this as b minus, and then we'll have bx0 plus cy0 q. What's further here is that we can do a little bit of rearrangement here so that we get this statement. We'll have b times 1 minus qx0, and then we will have plus c times negative qy0, negative qy0, like so. But this is also an element of S, which is a contradiction to the minimality of L. Because L not dividing B leads to a contradiction, we must assume instead that L divides B. So because L divides B, we can do a similar thing to show that L also divides C, and I'll leave that as an exercise to the viewer. Before moving forward, I think it's worth taking a review of what we've shown so far. We have our object S. This is the set defined as bx plus cy, where x and y come from the integers. And so far we've established an object L, which can be expressed as bx0 plus cy0. And we've established that we have a greatest common divisor between b and c, which we have called d. Furthermore, we have proven that L must divide b and L must divide c. So now what we have to do in the proof is to connect the object L with the greatest common divisor d to show that L must equal to d, and therefore the only thing that we can arrive at from this is that the greatest common divisor of b and c is the minimal element drawn from this set. Okay, because L is a divisor of b and c, our job now is to show that it must be the greatest common divisor, but all we know at this point is that it is a divisor of b and c. In other words, L must divide b and L must divide c, so L must be less equal to our greatest common divisor d. Because it either is just a divisor of d, which will always be less than the greatest common divisor, or it will be equal to our greatest common divisor. Now notice here that d is defined as the greatest common divisor of b and c. That means, since d is equal to the greatest common divisor of b and c, that means that we can express b as some multiple of d, and we can express c as some multiple of d, using beta and gamma as our integers that scale up d to equal b and c respectively. Now furthermore, we notice that since L is equal to bx0 plus cx0, we can replace the b and the c with our different ways of writing b and c. So L is equal to bx0 plus cy0, which is the same thing as writing beta dx0 plus gamma dy0. Now notice here that we can factor out a d from this expression, which will give us d times beta x0 plus gamma y0. That will give us d times beta x0 plus gamma y0. Or in other words, d divides L. And recall here that if d divides L, then something must be true. D must be less than or equal to L. Well, since L must be less equal to D and D must be less equal to L, we can look back to the previous propositions that say the only way for L to divide D and for D to divide L is for L and D to be the same thing. So we have a divisor, but that divisor must be a greatest common divisor. In other words, L is the greatest common divisor. Reason why that becomes important is because we can always express our greatest common divisor as a minimal element of this set, meaning we can express a greatest common divisor as a linear combination of two scale factors of the two elements that we're trying to find the greatest common divisor of. And what that does is it gives us a way to extend the Euclidean algorithm so that we can write that the GCD of something, we'll call this a small corollary, that the GCD of B and C will always be able to be written in this linear way, bx plus cy. I can always find a way to express the greatest common divisor as a linear combination of the two numbers that created that greatest common divisor. Now, before focusing on Euclid's algorithm to find the greatest common divisor, we need to look at a definition of what coprimality means. Coprimality just means that if I have two numbers whose greatest common divisor is 1, then they are considered relatively prime to each other. In other words, they share no common factors.